Hi everyone, my name is Hamed Gorgiara from UC Irvine. In this talk, I'll briefly introduce Yashme that is designed to automatically detect persistency races in the programs. This is a joint work with Hariju from UCLA and Brian Dembski from UC Irvine. During this talk, I present a new class of persistency bugs that we call a persistency race, which arises because of the interaction between compiler optimizations and persistent memory. Most programming language specifications provide compilers with the freedom to assume that programs are race-free, and other threads will not read from a non-atomic store until a release operation such as unlock is executed. This race freedom assumption allows compilers to perform different optimizations on non-atomic stores such as store tearing or store inventing. So the compilers only need to guarantee that the optimized code does not store to any memory locations that the original code didn't, and a store takes full effect before the next release operation. However, with persistent memory, system crashes can result in temporary values caused by these optimizations become persistent. For example, the program writes the value of quadruple f to variable x and then flushes this variable. X initially contains the value of quadruple a's in the memory. Variable x is non-atomic. Therefore, the compiler can freely decide to split this store into multiple store instructions x1 and x2. When the program is running, CPU executes the store x1 first and the cache is updated. If there isn't enough space in the cache writes back dirty cache lines to the memory and consequently x1 become persistent. In this state, if the system crashes, x2 store is lost since the CPU registers and the content of cache are volatile. In the post-crash execution, when the program reads from the variable x, it observes an invalid partially persisted value of double f double a. Variable x can be a pointer where this invalid value may lead to a program crash due to illegal memory access. We refer such bugs as persistency races. In general, standard compiler optimizations can lead to persistency races. For example, if we compile this program with GCC, a compiler with O1 optimization level under ARM64 architecture, a single write is split into 6 assembly instructions, and consequently, a poorly timed crash can cause to read a partially persistent value for x. Another case of persistency race is a common optimization by both LLVM and C++ for both ARM and x86 platforms, where the compilers replace a sequence of assignment to contiguous field with libc memory functions such as memset. These functions do not guarantee 64-bit atomicity, and consequently, this set of optimization may result in store tearing, leading to persistency races. We designed and implemented a new tool called Yashme to detect persistency races in the programs. Yashme is implemented on top of Jaru, which is a model checking engine to run programs and simulate crashes in them. Yashme's basic approach is to rely on cache coherency and flush instructions to ensure that non-atomic stores are fully persistent. The main challenge with these basic approaches is that detecting persistency races requires the crash to fall into a small window of execution after the store and before the cache line flush. In this example, since the crash is simulated outside of the detection window, no partially persistent value is observed by the post-crash execution with the basic approaches. However, if the crash was simulated inside of the detection window, the post-crash execution could observe partially persistent value of double f double a in variable x and report a persistency race for this variable. This requirement dictates aggressively injecting crashes in the great number of execution. The key idea in Yashme is to expand the detection window to make more races observable. In other words, Yashme does not rely on perfectly timed crash events to trigger races. Instead, given a target crash event, it derives executions that share a prefix with the pre-crash execution up to and including all the stores that the post-crash execution read from. This expansion technique enables Yashme to detect races in derived execution without the need to actually explore them. The idea is that when the pre-crash execution has flushed a store instruction, but the post-crash execution has not read from any stores after the flush, we can ignore the flush operation to find persistency races in the executions that we are not currently exploring. We evaluate Yashmi on a collection of data structure, including FastPair, CCCH, and 4 recipe benchmarks. In addition, we evaluate Yashmi on a set of real-world frameworks such as PMDK, Redis, and Memcache. In total, Yashmi found 24 persistency races in these benchmarks. Please refer to our full presentation for more details about Yashmi. Thank you.